We use butter right now. Like this much.
All right, let's go ahead and start chapter 17. Chapter 17 is alcohols and phenols. Phenols actually get a little more than just a mention in this chapter. We have jumped ahead from 11, which as far as we went, all the way to 17. We skipped spectroscopy, skipped electrophilic aromatic substitution, and phenols figure predominantly in electrophilic aromatic substitution reactions. But we're not going to talk about those until 235. You'll note that this is the image we saw of our Grignard reagent. Once again, Grignard reagents are going to figure predominantly in the synthesis of alcohols. Alcohols are basically the organic equivalent of water. They have an OH group, so does water. Water has two hydrogens. This simply has an alkyl or aryl group attached to the other end of our oxygen. This is glucose. You'll note that glucose has lots of OH groups. This is beta-D-glucose. D is an old stereochemical term relating to the stereochemistry at carbon number 1. This is beta. Beta refers to the stereochemistry at the anomeric carbon, which is this guy. Beta-D-glucose is a naturally occurring glucose. Ethanol, the alcohol of consumption, and this is cholesterol, OH group down here on the steroid nucleus. Common alcohols. This is isopropyl alcohol. Terbutyl. This is glycerol. Glycerol is a triol, so 3 alcohols on it. We just learned about allylic carbons, didn't we? This is an allylic carbon, and this is allyl alcohol. Likewise, this is benzyl group. This is benzyl alcohol. When we go to name an alcohol, we're going to follow our standard sets of rules. We want to draw a main chain that contains the hydroxyl group. We're going to show that it's an alcohol by dropping the E from our parent and putting in an OL. We want to give the hydroxyl group the lowest number. And we want to number our substituents, do them alphabetically, and of course we always shoot for our lowest number sequence. Standard sorts of rules. A simple example here. Here we have an alcohol. We want our parent to contain a hydroxyl group. So we'll let, whoops, where did it go? Gee. All right, well, let's just name this anyway. We have one compound. We're going to do a hexane as our parent. We're going to number at this end. We are going to have methyl groups at 4 and 5, hydroxyl group at carbon 2. The name that I wrote is the 2-hexanol. What we just said was you could also move this 2-ol down here in between the hexane and the OL. So you can put the 2 here or between the N and the O. All right, let's try our problem set again now. This is our cyclohexane diol. We said we had hydroxyl groups at carbons 1 and 3. They are both equatorial. That means they are on the same side of our ring plane. So we either have to call these cis, or we could call them Z. An acceptable name would be cis, 1,3-cyclohexane diol. Make sure that as you look at this structure, it is very obvious to you that this is cis or Z stereochemistry. Our next guy here. We have a benzene ring as a substituent. Remember, we call a benzene ring a phenyl group. It's pH, not phenol like the herb. Our parent chain here, 1, 2, 3, 4, 5. Therefore, it's a pentanol. Our hydroxyl group is going to define our parent chain. Therefore, this is going to be carbon 1 of our parent chain. Our phenyl group is simply a substituent out here on carbon 4. This last guy. We said that whenever we have a cycloalkane with two substituents on the same carbon, that we were going to define that as carbon 1. Well, that's true unless you have something that's higher priority. Remember the rule said, give the hydroxyl group the lowest number. Therefore, we're going to call this a 4,4-dimethyl cyclohexanol. You could put the 1 in, but you don't have to, because the 4,4 defines where the all is.
If you have a double bond in OH, does OH get
OH takes precedent. It's a higher priority group. Any questions? All right, well, let's just look at alcohols in general here. We know that the oxygen in an alcohol is actually a tetrahedral atom. We have hydrogen bonded in one sigma bond, we have our carbon bonded in our other, and we have two lone pairs of electrons. The chemistry of an alcohol is basically going to be concerned with these electrons. They can function as electron acceptors, therefore Lewis bases. I'm sorry. They can function as electron donors, that is Lewis bases. Our dihedral angle here between the OH and the CH or CO bond is 109 degrees. Remember, in a perfect tetrahedron, that would be 109.5. So this is pretty tetrahedral if you include the two unshared pairs of electrons. If you look at electrostatic potential map, not surprisingly, the OH bond is very polar. Here, this is the OH bond, this is the oxygen. Where the lone pairs are, you see a big red splotch. That's their high electron density. Again, this is low electron density, this is high electron density. This is also polarized here. The oxygen, being more electronegative, draws electrons away from the attached carbon. The fact that we have a polar OH bond here allows alcohols, just like water, to undergo hydrogen bonding. If we take a collection of alcohol molecules, remember we have two electron pairs on the oxygen. These can be donors for two hydrogen bonds. The OH group is a hydrogen bond acceptor. Alcohols, for their mass, are very, very high boiling, just like water. Water's higher than methanol. The reason is that water can do hydrogen bonds on both sides. Here we have the alkyl group, so this is kind of inert. But still, relative to its mass, alcohols are very high boiling. Reason for that is all of the hydrogen bonding in the network. Alcohols, just like water, are also acidic. If we look at ionization of ethanol, ethanol undergoes equilibrium ionization to give ethoxide and hydronium. This is just like water that you saw in general chemistry, where you took water and you made alkoxide and hydronium. As you recall from general chemistry, the expression for the equilibrium constant looks like this: products over reactants. For ethanol, this equilibrium constant is about 10 to the minus 16. Now with water, this was 10 to the minus 14, wasn't it? So they're very close. What this means in reality is that in this equilibrium, you have virtually none of this stuff relative to what you have here. So the equilibrium lies very, very far to this side, the side of products, with just a little bit of alkoxide and hydronium left over. Now the thing that determines how acidic a species is the anion here. The more stable the anion, the more you're going to shift this equilibrium to favor formation of the anion. That kind of makes sense, doesn't it? The more stable it is, the more you'll have. Well, we can stabilize an anion if we attach it to something that withdraws electrons. We disperse our charge, that stabilizes the anion. Therefore, if we put groups on our alcohol that stabilize that charge, that will be more acidic. This is just a simple list, starting here with alcohols, winding up with carboxylic acids. This was ethanol at 16, water 15.74, essentially the same. Methanol about the same. As we start adding things like fluorine groups that can withdraw electrons, because fluorine is electronegative, we see the pKa goes down. That means that the equilibrium constant here is about 10 to the minus 12 versus 10 to the minus 16. 3 trifluoromethyl groups, we're down to 5.4. That's a nice little strong acid. Acetic acid is 4.6. Trifluoroacetic acid, strong acid, about 0-ish. Let's look at a pair here. Let's just compare ethanol and trifluoroethanol. These differ in pKa values by about 4 units. If you think about trifluoroethanol, fluorine is very electronegative. It's going to suck the electrons out of this bond towards itself. In doing so, it removes electrons from the oxygen, and we wind up with a more stable anion. Ethanol can't do that. Electron density is pretty much localized on the oxygen. Pretty picture. Here we have our ball and stick. overlay the electrostatic potentials. This is our OH bond. Nice big red oxygen here. With trifluoro, you see we have less red, more stable anion, stronger acid. If you notice, the trifluoromethyl group here is yellow. This is nice and green. That means there's much more electron density here. Very interestingly, if you think about the polar covalent bonds in this molecule, they're opposite. The dipole along this bond goes this way, positive carbon, negative carbon. This one goes just the opposite, positive to negative, and here's our O minus. So just opposite dipoles on these two molecules. Phenols, the same sort of thing. Again, we're just barely going to mention phenols. Phenols turn out to be stronger acids than simple alcohols. That's because we can stabilize this anion by resonance. For phenol, undergoing equilibrium ionization, equilibrium constant would look like this, products over reactants. And for phenol itself, equilibrium constant is about 10 to the minus 10. It's 1,000,000 times more acidic than ethanol. And that's because we resonance stabilize the oxyanion. When you do chapter 14-ish, you will know that we can further stabilize this oxyanion by putting groups on the ring. This is what you will know in chapter 15, if we have done this first. Nitro group is a very good electron withdrawing group. If you put that in the para position, the pKa drops from about 10 down to 7. So that's 1,000-fold increase in acidity. Cyano is also electron withdrawing, so is a carbonyl and a chlorine. Down here, the methoxy group you'll see is electron donating, and the pKa goes up a notch. This is chemistry that you'll get next semester. You'll also see next semester that depending upon the substituent that's on your ring, you can direct substitution reactions, either ortho or meta, to the phenolic group. But again, that is next semester. Any questions on the concepts here? The more stable the anion, the stronger the acid. Alcohols are used a lot in commerce. Methanol is probably used the most, referred to as wood alcohol. Simplest way to make methanol is what's called synthesis gas. When you dig coal out of the ground and you partially oxidize it, you get coke. You also get a powdered coke that's in the big piles down by Calumet, is blowing everywhere from cracking petroleum. Well, coke is basically carbon. If you take coke and you take steam, hot water, lots and lots of pressure, you get a reaction that happens and you make carbon monoxide and hydrogen. Industrially, it's called synthesis gas. Depending on the catalyst you then show it to, you can make all sorts of things. A lot of it goes to making methanol. About 1.2 billion gallons of methanol are made this way. Now, ethanol we're used to making by fermentation. Industrially, however, it's really easy to make. Turns out that in Texas, there are gas wells that spew out ethene. If you simply take ethene and water, you make ethanol. Simple addition reaction. Hydration, roughly 300 million gallons are made this way every year. When they built this plant down in Texas, the government was so concerned that somebody was going to siphon off this stuff and make vodka out of it. All you do is add water. That they made them build the entire plant up on stilts so the inspectors could walk underneath it to make sure there was no hidden pipe going down and going to Mexico or wherever, where they would then convert this stuff to drinking alcohol. Turns out that even with all that, it still didn't work. Somebody still found a way. And a lot of this winds up in cheap vodka and cheap tequila. But it's just like fermentation stuff. Probably chemically it's better.
I only drink Patron, and well, they're a great loser.
Wow.
All right. We said we could make alkoxides at equilibrium. Yeah, that happens, but remember at equilibrium with ethanol, we get 10 to the minus 16th of our ethanol converted to alkoxide. That's not enough to use as a nucleophile in a reaction. Therefore, if we want alkoxide in a reaction, we have to make it 100% by one of these reactions. If we take sodium metal and we add it to something like methanol, we will get a sodium methoxide. 100% hydrogen gas bubbles off. If you added sodium to water, you would get sodium hydroxide. So the same sort of chemistry. Sodium amide, we saw this before. You add sodium to liquid ammonia. You form NH2 minus, very strong base. This deprotonates something like ethanol to form the sodium alkoxide. Here we're taking a methyl lithium. Now we saw we could make that last chapter by taking something like lithium bromide, bromomethane, lithium metal, react that, we make methyl lithium. Very strong base, converts this to the lithium alkoxide. All of these are very standard reactions. These are used widely as nucleophiles in substitution reactions, things like that, or as bases in elimination. Any questions? All right, reactions that make alcohols. We already know these from way back in chapter 8-ish. If we take a simple alkene, we dump in acid and water, we can make an alcohol. We know that this is going to be a stepwise reaction. We know that we're going to have a carbocation intermediate. We know that whenever we have a carbocation intermediate, we can get rearrangement. And finally, the regiochemistry we wind up with, we call Markovnikov. So that's what we already know. Going to form a carbocation. It will rearrange to the most stable carbocation. Alcohol, or OH, will add to that carbocation. We know that there's a more civilized way to do this, and that is to use mercuric acetate. We also get Markovnikov regiochemistry, but no rearrangement. So we know this. We also know we can make anti-Markovnikov alcohols from alkenes by hydroboration oxidation. This is a concerted reaction. We get cis addition of the OH group and the hydrogen. And once again, it's anti-Markovnikov. Finally, we also know that we can make 1,2-diols by taking an alkene, either the permanganate or osmium tetroxide, and we have cis addition of our hydroxyl groups. So this is what we know. Now in this chapter we have some new reactions as well. Our first set of new reactions are going to be reductions. In a reduction reaction, we're going to take a carbonyl compound and we're going to convert it to an alcohol. What we're going to do here is add a hydrogen to the carbonyl carbon. There are two reagents that we'll talk about. One is sodium borohydride, BH4 minus. It's water soluble, it's a salt. We add borohydride, then we acidify, and we wind up with an alcohol. Aldehyde, add H minus here, we get a primary alcohol. We can also do this with lithium aluminum hydride. Now we'll see lithal in a minute. Very, very nice reagent. It does have one personality problem, however. If we do all this chemistry on a ketone instead of an aldehyde, we add our hydrogen to the carbonyl carbon, and now we get a secondary alcohol out of our ketone. We've already seen our Grignard reagent, haven't we? The alkyl carbanion adds to the carbonyl, and we get an alcohol. If we have an aldehyde, we get a secondary alcohol. If we have a ketone, we get a tertiary alcohol. We'll talk more in detail about this later. Our reduction here, sodium borohydride or lithal. And again, we've talked about our Grignard reactions. Aldehydes, secondary, ketone, tertiary. All right, let's go and look at reductions with something like lithal. Lithium aluminum hydride is lovingly referred to as lithal. It's a very nice, very selective reagent. This is a model representing the lithium atom. Our aluminum is in the middle here. We have 4 hydrogens attached. All of these hydrogens can be donated as hydride. Now, a hydride is a hydrogen and its pair of electrons. So it's an H minus. Just like we had the Grignard anion adding, here our H minus is simply going to add to the carbonyl. This is our tetrahedral intermediate. When we take this tetrahedral intermediate dump it into water, this converts to the alcohol. Now, lithium is a very, very versatile reagent. Lithium, we can react with epoxides, aldehydes, ketones. We'll see esters and acids. We can also react it with nitriles and azides. You'll do that next semester. But it's a very, very versatile reaction. Again, all you're doing is donating H- to your electrophilic center. Now, we can get the same products from borohydride or from lithium. If you have really no difference in what you're working with, borohydride is what people tend to use. Problem with borohydride, as you see here, we have a ketone and a double bond. The borohydride will not only reduce the ketone, but it'll also do both, reduce the ketone and the double bond. It does it about equally. That's bad. Lithium, on the other hand, does this reaction essentially quantitatively to get this stuff. And that's good. Nonetheless, if there is no real difference, if you don't have other functionalities that can get in the way, you always use borohydride. Why is that? Because lithium aluminum hydride is extremely flammable in air. It reacts with water virtually instantly. Produces a great amount of heat, produces hydrogen gas, and it explodes. So it's nasty stuff. You'll note that we have to use ether with lithium. Now, ether is an extremely explosive solvent anyway. So you have something that is flames the moment it hits moist air, and you have a solvent that explodes if it's flamed. Let's look at an example of this. This is a person holding a little beaker here that has regular ether in it. Now, if I went in the lab over there and I pulled out a bottle of their ether, and we use that in a lithium experiment, this is what would happen. You must be absolutely compulsive that your ether is 100% dry. Ether can contain up to 5% water. Once you open the container, water sucks in there like mad. So she's going to add this stuff to this beaker with some lithium in there. Now, you don't want this to happen in lab, do you? Lithium is a wonderful reagent. It's nice, it does all sorts of great chemistry, but you really have to know what you're doing before you mess with it. We won't ever use it in lab here.
That'd be awesome for a fireplace.
Yep.
Minus the
All right,
gas.
let's do some one-step syntheses here.
Exhausting.
Look at these products. We're doing all of these with lithium aluminum hydride. Then we're working up with aqueous acid. What carbonyl compound do you need? Well, your logic here is very, very, very simple. You say, okay, here's the hydroxyl group. That carbon used to be a carbonyl carbon, right? All we did is convert it to an alcohol. Therefore, you simply redraw this. This carbon used to be a carbonyl. Our next reaction, we're making a secondary alcohol here. Once again, all you have to do is look at this and say, this right here used to be a carbonyl carbon. It is now a secondary alcohol, therefore this was a ketone. And our last one here, we are making a methyl cyclohexanol. Once again, it's a secondary alcohol. This used to be a ketone. Our reactant simply looks like this. Now we're adding H minus, aren't we? H minus is little. H minus can slip in through the top or through the bottom. So we will actually wind up with stereoisomers at this point. Any questions? All right, let's stop here and go and start working on our turkeys or whatever. And next Tuesday, we will come back. We will finish up chapter 17, and then we'll start working on some problem sets. I will put problem sets up on Blackboard. Maybe I'll email you a PDF or whatever. Print those out, and we'll work those after we finish this chapter. Have a nice Thanksgiving, guys, and we'll see you in a week.